That's awesome.
Yeah.
Just a quick question before we start. Is it the right time or no to ask?
We're kind of starting now. You can ask, right?
No worries.
Hey everyone. Hello. All right, good morning. So before we start today, we have some lovely people from DevSoc who are going to talk to you about their society and their projects. And yeah, if you're interested, then you can apply. All right?
So, hello everyone. Good morning. I know it's Tuesday morning lecture, so hope everyone's listening week. As Tim said, we're from DevSoc. As a society, we mostly do project development. So recently, there's been lots of websites, as you can see up there. We have some timetable planners, notical circles, some course view websites, union electives, and you can find a free room, free rooms. And we also have a data structure and algorithms visualizer, or structs, which Tian and Sylvia will talk about in a brief second. And it's pretty much custom made for 1511 and 2521. So hopefully it will be useful for you in this course.
Okay, hi guys, I'm Sylvia and I'm the front-end director of Struts for 2025. And so today, right, the first question, what is Struts? So Struts is a data structures and algorithms visualizer that's custom made for 1511 and especially 2521. And at the moment, as you can see, I'm just gonna run this video. Oh, sorry. Oh, and at the moment, we currently support linked lists, binary trees, and sorting. So definitely check us out if at any point of the course you're struggling to connect the intuition with the code. I've used it personally back then as a second year, and it was super helpful. So I definitely recommend it, not just from a a developer's point of view. And but on top of the existing features, we're also going to release and develop some new features this year. And yeah, my co-director Tian will talk about them.
So our newest feature, the debugger, is designed to be a bit better than GDB, where you can run your own code and take a look at what's going on inside the memory. We are doing our best with linked lists right now, so if you have a linked list code and you run some lines, like you step through some lines, ideally you get a little linked list on the bottom right, and that's not hard-coded, that comes straight out of your program. So if you change the numbers in your program and rerun it, it will update there.
And this year, since we're currently in the subcom recruitment season, this year we actually have some really grand goals and ambitions, and one of them includes implementing graph visualization. So that's going to be a huge improvement for the project and very helpful for future 1511 and 2521 students. And the debugger currently, to access the debugger, you have to type in structs.sh/dev. But we're also planning to officially release it this year, so there will probably be a big button, on the front page, so it's easier for everyone to access. And we're also developing many more features. And if you guys have any suggestions for us, again, we're currently in the recruitment season. Please feel free to, apply for us. And that naturally leads to the next topic, the DevSoc experience. So these are photos of the Struct subcommittee during our social events and dev sessions last year. We hosted dev sessions once a week, and we met up for dinner, and we went to marathon parties, and we went on road trips. It was a very, very fun experience. So if you're looking to contribute to Structs and make some friends, definitely consider joining us. It's so fun. And yep.
Yeah, so as Sylvia just mentioned, we do have our subcom applications open right now, so if you want to work on any of the projects you saw on the first slide, please feel free to apply. We also have some operations supports like HR, events, sponsorships, if you want to get your feet into that kind of area. We also have marketing if you're kind of an artistic creative person. Yeah, so perhaps we also have an introductory website training program, which just closed, but we'll be opening it in terms 2 and terms 3 if you want. Additionally, in the next 3 to 5 weeks, we'll have some career-based workshops. So if you want to have some look over your resume, get some interview practice, whether that be technical or behavioral, we have workshops coming up in, I believe it's 5, 7, and 9. So yeah, keep looking out for that. And one final thing. Yeah, we have our alumni panel tonight, 6 a.m. We have free food, we have pizza, this will be on for everyone. Come meet our alumni, like our former execs and directors that are working in basically Australian big tech. So we have Atlassian, Canva, Snapchat, TikTok, all represented there. So if you have time when you're on campus today, join us at 6 to 8. I have been advised that the location might change, but if you look at our Insta or Discord, you will be able to find the location. Thank you, and good luck with 251.
All right, thank you, DevSoc. Okay, so now we're going to get into our content for this week, which is sorting algorithms. Okay, so why are we covering sorting algorithms this week? So last week we talked about recursion, we also talked about complexity analysis, and I think sorting algorithms is a very nice topic for us to be able to analyze a bunch of different sorting algorithms and analyze their complexity and understand how different algorithms have different properties, so different time complexities, space complexities, and other properties specifically related to sorting algorithms. Okay. So let me just double check that the live stream is on. Cool, it is. All right, so let's begin. So why do we care about sorting? Right, so sorting is a really important operation because, first of all, as we saw last week, if you have a sorted array, then you can search more efficiently, right? Instead of using linear search, where you have to start from the beginning of the array and then just keep looking further down until you find the item, you can use binary search, right, which has a time complexity of O log n, right? And then we also care about sorting because sorting provides a very useful intermediate for other algorithms, right? So if you can imagine you have an array where you need to remove duplicates, right? Or you want to count duplicates, right? If you have a sorted array, then it's much easier to do that, right? If you just think about it. And then if you have two arrays or two collections that you want to merge, right? Having both of these arrays be sorted or sorting them beforehand makes it much easier to merge them into a single sorted collection. Okay, so right, when we are sorting, in this course we're going to be mainly focused on arrays, right? So sorting arrays, but keep in mind that you can also sort linked lists, you can also sort files, and so on. Right? And when we're sorting, in the real world, usually we're not going to be sorting just individual integers, right? Because that's not very useful. Usually in the real world, you have items that contain a bunch of different fields, a bunch of different properties. Think, for example, of a student, right? A student might have a ZID, might have a name, might have some courses that they're enrolled in. And we want to sort those items or sort those structs by a specific property, right? So that property is what we call the key, okay? So if we sort by the ZID, then the key would be the ZID. If we're sorting by name, then the key would be the name, right? So that's what we mean by key, and we'll be using that term throughout the lecture. Okay, and one kind of obvious thing is that when we're sorting an item on something, right, we have to use an ordering relation, right? What I mean by that is that we need to have a way to compare the two items to tell if one is less than or greater than the other one, right? So if we're sorting by number, right, then the numbers are going to be sorted numerically. If we're sorting strings, so for example, if we're sorting by name, right, then the strings are sorted alphabetically, right, or lexicographically. Okay, so what we're going to do in these lectures is we're going to be viewing our problem as sorting an array of items, right? So in the code, we're going to be writing our array as an array of items, but the items could be integers, they could be chars, they could be doubles, and they could be strings, they could be structs, right? So they could be all sorts of data types, and we're sorting the items based on a key, okay? And depending on what the item is, the key could be just the entire item, right? If the item is just an integer, if the item is a struct, then the key might be a single field in that struct. So here's an example of sorting, right? So we have an array of students, and each student has a ZID and a name, and we want to sort by, we can sort by either ID or name, right? So if we sort by ID, then we see that if we go down the array, there will be an increasing order of ID, right? But the names are not going to be sorted, right? Because we're sorting by ID. Meanwhile, we can sort, if we sort by name, then if we go down the array, we can see that the names are in alphabetical order. Okay? Cool. And the view of sorting that we're going to take in this lecture is we're going to be sorting the array between two indices, right? Between low and high. So low is the index of the leftmost item that we want to sort, and high is the index of the rightmost item that we want to sort. Okay, and if you want to sort the entire array, then low would be 0 and high would be n minus 1, right, where n is the size of the array. Okay? And the reason why we are framing our sorting problem like this, like sorting between low and high, is that when we get to some of the sorting algorithms, they're going to be recursive, right? And what that means is that we'll be sorting different parts of the array recursively. And that's where passing in a low and high index is going to be useful. Okay? Cool. So here are some examples of sorting algorithms. Right, so we're not going to look at all of them, and there are a ton more sorting algorithms than what I've listed here, but here are some main ones. So we have some elementary ones, like selection sort, bubble sort, and insertion sort. We have some sorting algorithms which are divide and conquer algorithms, which sounds cool, so we'll get to what that means when we actually cover them, but these are merge sort and quick sort. And then we also have some non-comparison based sorting algorithms. So the algorithms here, so the first 6, are what we call comparison based. And we also have sorting algorithms that don't rely on comparisons, like radix sort. And we'll look at that one probably tomorrow. And there was a question asking the sorting mean we sort from lowest to highest. Yeah, so if we don't mention what we're sorting, like whether we're sorting in ascending or descending, just assume that we're sorting in ascending order. Okay, and of course, we're going to be looking at these sorting algorithms, but we're also going to be analyzing them, right? So when we analyze sorting algorithms, different input orders can result in different run times, right, or different time complexities, right? So that's why it's important to look at different types of inputs, such as random order, right? So if your array isn't sorted in any particular way, then how well is the algorithm going to perform? If the array is sorted, right, how well does the algorithm perform, right? Does the algorithm take advantage of the fact that the array is already sorted, right? And another one is reverse sorted. So if the array isn't sorted, it's not randomly sorted, but it's kind of reverse sorted, then how well is the algorithm going to perform? Okay, and yeah, when we're analyzing sorting algorithms, we're going to consider these three variables, right? So there's n, which is the number of items in the array, or the part of the array that we are sorting, and we're going to consider the number of comparisons that the sorting algorithm makes, and also the number of swaps that the algorithm makes. Okay, and in addition to the time complexity and the space complexity, we're also going to look at a few properties related to sorting algorithms specifically. So these are stability, adaptability, and in place. So whether the algorithm is in place. So what do these mean? So first, for stability, stability is the question of whether the sorting algorithm preserves the relative order of items with equal key, right? So what I mean by that is, suppose we have an array of students again, and we have a bunch of people with the same name, right? So here we actually do have two students with the same name, John, right? And if our sorting algorithm is stable, then it will keep the two Johns, and suppose we're sorting by name here, then a stable sorting algorithm is going to keep the two Johns in the same order after sorting. So that means the 5151515 John is going to appear before the 5555555 John. Okay, so that's what stability means. And here is the formal description of stability. And what this is saying is a stable sort preserves the relative order of items with equal keys. Okay, and a stable sorting algorithm, okay, so there's a difference between a stable sort and a stable sorting algorithm. A stable sort is like what happens if you sort the array and it happens to preserve the relative order of items with the same key. A stable sorting algorithm will always perform a stable sort, right? So it's possible for an unstable sorting algorithm to produce a stable sort, but it's not guaranteed. So here are some examples of stability and instability. So here we have an array of cards, right? Each card has a value and a suit, right? And if we sort these cards by value, then if we do a stable sort, right, then since we have multiple 4s and we have multiple 6s, they're going to remain in the same relative order. Okay, so the 4 of diamonds appears before the 4 of spades in the input, so they're also going to appear in that order in the output. And the 6s are also going to remain in the same relative order. Okay, so the 6 of clubs is going to appear before the 6 of hearts. Okay, so and here is an example of an unstable sort. Okay, so here we have a 6 of clubs appearing before a 6 of hearts, but if we do an unstable sort, then one possible result is that the 6 of hearts or the 6s have swapped order, right? So they're not in the same order afterwards. So the 6 of hearts appears before the 6 of clubs, right? Another possible outcome is that maybe the 2 4s have also switched orders, but this is already unstable, right? Because the 6s have switched around. Okay, and when do we care about stability, right? So first of all, when we are sorting the same array multiple times, then stability might be important, right? Because maybe we want the second sort to preserve some ordering that was produced in the first sort, right? And some sorting algorithms do rely on stability, like erratic sort. Okay, so that's important. For example, so this isn't erratic sort, but here's another example of why we might care about stability. So suppose we have an array of names, right? We have an array of first names and last names, and we want to sort the names, right? What we want to achieve is that we want the array to be sorted by the first name, but if 2 people have the same first name, then we want them to be ordered by last name, okay? So one way you can do this is you can first sort the array by last name, right? And then you sort the array by first name, right? So we sort by last name and then first name, not the other way around, because if we sorted by first name and then last name, then in the final array, it's going to be ordered by last name, right? Which isn't what we want. So we sort by last name first and then first name, right? So here, notice that we have multiple people with the same first name, right? We've got 2 people with the name Alice, and we've got 2 people with the name Andrew, right? And if we want to achieve a sorted array where they're sorted by first name, and then if 2 people have the same first name, they're sorted by last name, then you need to make sure that your second sort is stable, right? Because the first sort makes sure that people are sorted by last name, right? Look at this, like Bennett, Hatter, Renzella, Shepard, Taylor, Wonder, right? And then if the second sort wasn't stable, right, then since we have 2 people with the same first name, Andrew, right, an unstable sort might switch them around, right? It might put Andrew Taylor before Andrew Bennett, and then the array is not going to be sorted the way we want. Okay, so that's an example of when we might care about stability. Okay, but when does stability not matter? So first of all, if all the items have unique keys, right, then it doesn't matter whether the algorithm is stable or not, right, because there aren't any duplicates that we can switch around. Right? Example of this is if we're sorting by ZID, right? So we're sorting students by ID, right? We already know that every student has a unique ID, right? So it doesn't matter whether the algorithm is stable or not, it doesn't matter. Okay, and another example is if the key that we're sorting by is just the entire item, right? And an example of this is if we're sorting an array of integers, right? So if that's all we're sorting by, if the items are just integers, then even if we have duplicate integers, it doesn't matter if the algorithm is stable or not because we can't tell them apart from each other, right? They look the same. Right? So two 15s look like look the same. And we have a question about where the lecture hall is. You can check the timetable, but we're in Matthews A. Okay, and the second property we are interested in is adaptability. Okay, so what is adaptability? So adaptability is whether the sorting algorithm takes advantage of pre-existing order, right? So does the algorithm take advantage of existing order in the input? So maybe if the array is already ordered, right, then the sorting algorithm will be faster or much more efficient. Okay, and for a sorting algorithm to be adaptive, it has to have something about it. So the algorithm has to have something about it that makes it sort sorted inputs much more quickly. Right? So it's something about the nature of the algorithm. Okay, and we'll look at some examples of that. Okay, and one thing to be careful of is just because a sorting algorithm sorts sorted input faster than it sorts random or reverse inputs, doesn't mean that it's adaptive, right? So, for example, suppose your sorting algorithm sorts sorted inputs about 50% faster, right, than reverse sorted input. That doesn't necessarily mean that it's adaptive, right? So what we need is for the algorithm to be much more efficient. So not just the constant multiple, but we expect the sorting algorithm to have a better time complexity when sorting sorted input. Right, so what I mean by that is, here is an example of an algorithm which isn't adaptive, right? Although it does, so here is, on the x-axis we have input size, on the y-axis we have the time it takes for the algorithm to run, and we see that it sorts sorted input quicker than random input, right? So for sorted input, it takes about 60% of the time, or 50 to 60% of the time it takes to sort random input. Now this is a constant multiple difference, right, between the two different types of input. And when the timing results are like this, we don't say that the algorithm is adaptive, right, just because it's a constant multiple difference. But here's an example of data for an adaptive sorting algorithm, right, where the two curves are fundamentally different, right? They have different shapes. But for the sorted input, the sorting algorithm actually takes a linear time, so O(n), to sort. And for random input, the sorting algorithm takes something that looks like an O(n) squared amount of time to sort. Right, so if our timing results are like this, then we can say that the sorting algorithm is adaptive. Okay, so the last property that we're interested in is in place. And what in place means is that the sorting algorithm doesn't store the items in a temporary array. Okay, it just sorts the data using the original array by maybe swapping things around or shifting them, right? So it doesn't store items into a temporary array in order to organize them or anything. It doesn't use temporary arrays. Okay, so these are the three properties. So does anyone have any questions about these? Okay, lastly, we're going to talk about how we're going to implement our sorting algorithms. So what are the data types that we're going to use? So what we're going to be implementing is this function prototype, right? So it's going to be a function that takes in an array of items, right, where the item can either be an int, it can be a char star, a string, it can be a struct, or something else. And as I talked about before, we're sorting between low and high, right? So these are indices. And what's going to be useful is a function that swaps two items, right? So here we have a swap function that takes in the array of items and two indices to swap. Okay, so the item can be many different things, from int to char star, right? So if we want to sort an array of integers, then what you can do is use typedef to typedef an int to item. Right, so what typedef does is it allows you to give a type a new name. Right, so if I say typedef int item, then what I'm saying is that instead of writing int, right, I can write item in my code, and they will mean the same thing. So item would be the same thing as int. Okay, and if instead we had an array of strings, right, and we wanted to sort this array, then we can say typedef char star item. What that means is that instead of writing char star, I can write item instead. Okay, so this is nice because it allows us to write a generic sort function that just takes in an item type, and then depending on what the user has typedefed to an item, right, we can sort different data types. So we can sort by int, we can sort by char star, we can sort by other data types too. Okay, so in addition to these typedefs, we also need a generic way to specify how to compare items, right? Because with integers, right, you can just compare them using the less than sign, right? And less than or equal to, greater than equal to, greater, right? But if you're sorting strings, you can't use less than, right? Or less than or equal to. That's not gonna work, right? So you're gonna need to define how to compare two keys, right? And here's how we would define it for integers. Okay, so if your items are just integers, right, then you can define what we call macros for less than or equal to, greater than or equal to, greater than. So for example, what this line is doing is it's saying that in the code, whenever we see the words, whenever we see LT, and then two arguments, so when we see something that looks like a function call to LT that takes in two items, that's going to be the same thing as getting the key of the first item and then using less than to compare it to the key of the second item. Okay, so yeah, these are what we call macros, and they're kind of similar to hash defines, except they take in arguments. Right? So you've probably used a regular hash define in COMP2521, where you hash define and then you type a word, right? And then you type a number. And what that does is when the program is compiling, whenever it sees the word in your code, it just replaces it with the number, right? So macros are like your hash defines, but they take in arguments, right? So here, for example, when the program is compiling and it sees, so here we have a macro called LT, right? When the program is compiling, when it sees a function called to LT, or something that looks like a function called to LT, then it will replace that macro with whatever is on the right. So it'll paste in this expression. Okay. So we have a question about, can typedef be alternatively used for hash define? So we can't use typedef instead of hash define because typedef we use to define names, new names for types. Right? So they serve different purposes. And we'll release the lecture code after the lecture. Okay? Yeah. So another question is about what is the point of the key macro? So the point of the key macro is what happens if our item is not just an integer, but it's a struct, right? And we're sorting by a specific field. What we can do is we can use the key macro to extract the key from the item. Okay. In this case, it's not very useful because the items are just integers. But on the next slide, I think there is an example of where we're sorting a struct by a specific field. Right? So here we have items which contain a name and a course. Right? And then if we want to sort the structs by name, then we have a key macro which takes an item, right, and then extracts the key from it. So extracts the name field. And then since these names are strings, we have macros which use strcomp, right? So we're not using just less than or greater than, we're using the strcomp function which lets us compare strings. Okay, and we have a question about what happens if we try to give macros an incorrect argument. So if we do that, then the program won't compile. So that's what will happen. And you'll get a compilation error. Because like hash defines that you used in COMP2521, macros are similar. So when the compiler sees you use a macro, it just pastes the definition of the macro there. And then since you've passed the wrong thing, it's not going to compile. How does the macro know what the type of the arguments are? So it doesn't know. When the program is compiling, it'll paste in the definition of the macro whenever it sees that you use one. And then it'll check the arguments of whatever you've passed the macro. Right, so this isn't supposed to be a lecture on macros. You're not going to need to write macros yourself in the course, but they'll be in the lecture code. So this is just for you to understand the code when you go and take a look at it. Okay, and yeah, that's the end of the intro to sorting. So what we're going to do now is take a look at some elementary sorting algorithms, specifically selection sort, bubble sort, and insertion sort. Okay? So let's look at selection sort first, the most straightforward sorting algorithm. Okay, so how selection sort works is we first find the smallest element in the array, right? And then we swap it with the first element, with the leftmost element, okay? Because that's where the smallest element should go, right? Then we find the second smallest element and then swap it with the second element in the array. So this is the this would be index 1, right? Because that's where the second smallest element should go, right? And then we just repeat the process, so find the third smallest element, swap it with the third item, and then eventually, once we've swapped most of the items into place, we would find the second largest element, swap it with the second last element, and that's it. right, then the array is sorted. Okay, so this is a really straightforward sorting algorithm, and here is an example. Right, so in the first iteration, can someone tell me what two items we're going to swap? Yep, so we're going to swap 4 and 1, right, because 1 is the smallest item and it belongs where the 4 is, so we're going to just swap them around. Okay, so we're going to swap them. Okay, in the second iteration, we're going to look for the second smallest item, which is 2. Right, then we're going to swap it with the 4. Right, in the third iteration, we're going to find the next smallest item, which is 3, and we're going to swap it with the 7. Right, in the next iteration, we're going to find the next smallest item, which is 4, swap it with the fourth item, which is 7. Right, then we're going to find the 5, swap it with the 8. Then here's an interesting case where we're looking for the next smallest item and it's already in the correct spot, right? So we do end up like swapping it with itself, and that's perfectly fine. Okay, and in the next iteration, we find the next smallest item, which is 7, and then we swap it with the 8. And then the array is sorted. Okay, and we have a question about whether you'll need to memorize the code. So you won't need to, because we'll be providing the code for the main algorithms in the exam, right? So you don't need to memorize the code, although a nice exercise would be to try and implement the code yourself, right? I think that would make you better at coding in general, right? If you can code these up by yourself. Okay, and here's the code for selection sort. So notice here that we're using LT to compare two items. Okay, so how does this code work? So we have an outer loop. So the outer loop controls how much of the array we've sorted so far. Right? So it's going to start off at low, right? And then we're going to keep incrementing it until high. Okay? And for every iteration of the algorithm, we're going to find the minimum item, right, out of the part of the array that we haven't sorted yet. Right, so we're going to initialize min to be equal to I, right, and then we're going to loop through the rest of the array to find what the minimum item is, right, out of the remaining part of the array. Okay, so int j equals I plus 1, and then j loops all the way up to high, and if the item at index j is less than the items at index min, right, which is what we're using to keep track of where the minimum item is, then we set min to be equal to j, okay? And after the inner loop has completed, we will have figured out what the minimum item is in the rest of the array, and we're just going to swap it with the item at index I, okay? So that's how selection sort works. And we have a question about hash defines, about whether it's like dictionaries in other languages. So they're not really the same thing. So in Python, there are these data structures called dictionaries, but they're not the same. We have a question about if min, isn't min equals items j? So why do we have min equals j instead of min equals items j? So that's a good question. And the reason is we're using min to keep track of the index right, of the item, the index of the smallest item. Right. The problem with just storing the item itself is after we found the minimum item, we won't know where it's stored, right? So we can't swap it. Right? We don't know where to swap the other item to. But that's going to be the problem if we just say min equals items j here. So we're using min to keep track of the index of the smallest item. What does LT in the inner if statement mean? So LT here is our macro for less than, right? So this is what we use to tell whether items j is less than items min. So the question here is we're switching indexes of the items. So on this line where we call swap, we're not swapping. So we're passing in two indices, but what the function does is it swaps the items at those indices. So there was a little bit about this at the end of the previous set of slides. So that's what the swap function does. Okay, so it takes the array, it takes two indices, and it swaps the items at those indices. Can I explain what the if statement is? Yes, so what this if statement does is it checks if the item at index j is less than the item at index min. And if it is, then we found a new minimum item, right? So we set min to j. So we're saying, oh, I found a smaller item, and it's stored at this index, at index j, okay? Is low a number or an index? So low is an index, right? And high is also an index. So we already covered this in the intro lecture, but low is the index of the leftmost item that we're trying to sort, and high is the index of the rightmost item. Okay. And with macros, you don't need to worry about them right now. Right? You can imagine that these are function calls. That even though macros aren't technically function calls, for now you can think of them as function calls. Here, you're checking if items j is less than items min. Okay. So let's analyze selection sorting. So what we're going to do is we're going to count both the number of comparisons that the sorting algorithm makes and the number of swaps. Okay, so in the first iteration, let's think about how many comparisons we need to do. So first of all, we take the first item in the array to be the minimum item. So we assume that's the minimum, and then we scan the rest of the array, so that's n-1 items, to see if we can find any smaller items. Right? So that's going to take n-1 comparisons to find the minimum item in the first iteration. Okay, and at the end of that iteration, we perform one swap, right, to swap that minimum item into the first slot in the array. Okay, in the second iteration, we make n-2 comparisons, right, because the smallest item is already in the right spot, and now we're just looking at the rest of the items, the remaining n-1 items. Right, and to find the minimum item among those, it's going to take n-2 comparisons. And at the end of that iteration, there's also going to be one swap. Okay, and in the final, so you can kind of see a pattern emerging, right? In the third iteration, it's going to take n-3 comparisons to find the third smallest item, and then one swap. And finally, in the final iteration, it's going to take one comparison, right? And then we're going to make one swap. Okay, so in total, the number of comparisons is going to be n minus 1 plus n minus 2 plus n minus 3 plus blah, blah, blah plus 1. Okay, so that's going to be equal to half times n minus 1. Okay, so it's just an arithmetic sum. And that expression is O of n squared. Right? So if we remember, we take away the lower order terms and constant factors, that's going to be O of n squared. And the reason we're using the word cost here, well, it's kind of because, I mean, every operation, there is a cost, right? A cost in terms of it takes time to perform the operation. So it's kind of like a time cost for the algorithm. Okay, and the number of swaps is equal to n minus 1, because we have n minus 1 iterations. Okay, so that's the analysis of selection sort. So we see that time complexity of selection sort is O(n) squared. And there's a question about, do you need to know how to go from the sum of n minus 1 and so on to the right-hand side? So do you need to know this summation? So I think it would be helpful to know. Yeah, whenever you have a sum, like a triangular sum, where it's like 1 plus 2 plus 3 plus 4 and so on, I think it's good to know what that equals to. But yeah, if you have a triangular sum, then that's going to be, there's going to be a square in there, right? An n squared in there. Is the summation going to be tested on? Just asking what 1 plus 2 plus all the way up to n equals to, we're not going to ask you on that, right? But we're going to ask you to, we might ask you to analyze an algorithm where you might need to perform such a sum, right? So I think it would be useful to know. Okay, so yeah, that was the time complexity analysis. Now in terms of space analysis, so space complexity, so that's the amount of additional memory that the algorithm uses. It doesn't use any additional memory aside from a few variables, right? So we use a few extra variables for I, min, j, and we do call a couple of functions, but they also only use a few variables themselves, right? So this algorithm uses O1 memory. And in terms of the other properties, so stability, turns out selection sort is unstable, right? And initially it might seem that it is stable because when you're going through and finding the minimum item, we're using less than here, right? Which means that if we're scanning through the array and we see an item which is equal to the minimum item that we found earlier, then we're not going to replace our minimum with the new item, right? We're going to keep the original one. And from that, it might seem like selection sort is stable, but it turns out that it isn't, right? Because of the long-range swaps that the algorithm does. Right, so the problem isn't the item that you're swapping into, so it's not the item that you're swapping into the first index during the first iteration. You're swapping the smallest item into the first, with the first item, the second smallest item with the second item, and so on. So the problem is the other item that you're swapping, right? So for example, suppose we have these 3 items that we're trying to sort, right? So these 3 cards, and during the first iteration, you're going to be swapping the 2 with this 6, right? The 6 of clubs. So what ends up happening is the 6s are going to end up in the wrong order, right? So they're going to be swapped around. And they're not going to be in the same order as when you started. Okay, so in summary, for selection sort, first of all, it's unstable, right? And another thing is that it's not adaptive, right? The algorithm doesn't do anything to help sort sorted arrays quicker, right? It always needs to loop through the entire array to find the smallest item, right, at each iteration. Okay, and selection sort is in place. Okay, so it doesn't use any temporary arrays. And there was a question about if I can go over this again. Yeah, so during selection sort, so suppose we're sorting these cards by value, right? So during the first iteration, we find the card with the smallest value, so that's going to be 2, right? And we swap it with the first item in the array, right? So that's going to be the 6 of clubs. Right? So if we swap these 2 cards around, then now the 6s are not going to be in the same order anymore. Okay, and if you can visualize it during the second iteration, the smallest item we're going to find is the 6 of hearts, right, where you're just going to end up swapping it with itself because it's already in the right spot. And that's the end of the sorting algorithm. Okay, so yeah. Okay, so that's selection sort. So what we'll do now is we'll take a 5-minute break, right, and then when we come back, we'll talk about bubble sort and insertion sort. Okay. Okay, so let's resume. Yep, I just remembered that, yeah, so there were some popping sounds in the previous lecture. I'm not sure about the exact cause. I think one might be the fact that the microphone is too loud. So I'll try lowering it a little bit. And another possible reason is that it's something about the microphone like rubbing against my shirt. So I'll be a bit more careful. Maybe I'll try to stand more still. Okay. Cool. So let's now talk about bubble sort. Okay, so the idea of bubble sort is that it's going to make multiple passes through the array from left to right. Okay, and on each pass through the array, it's going to compare adjacent items. Right, so during the first pass, it's going to compare index 0 with index 1, index 1 with index 2, index 2 with index 3, and so on, all the way to the end. And if, while it's comparing these adjacent items, it finds that they're out of order, so the left item is greater than the right item, it's going to swap them. Okay? And the effect that this has is that larger elements are going to bubble up the array, right, until they meet a larger element, and then that larger element continues to bubble up the array. Okay? And a special thing about this algorithm is that it swaps, it stops if during a particular pass it doesn't make any swaps. Okay? So bubble up here means it kind of keeps swapping its way up the array. Okay, so that's what it means. And yeah, if during a particular pass the algorithm doesn't swap anything, then that means the array has to be sorted. Right? So here's an example of bubble sort. So during the first pass, we're going to compare 4 and 3, right? So 4 and 3 are out of order, and that means we're going to swap them. Okay, so now we have 3 and 4. Then it compares 4 and 6. Right now 4 and 6 are in order, so we don't swap them. Next we compare 6 and 1. Right, 6 and 1 are out of order, so we swap them. 6 and 2 are out of order, so we swap them. And 6 and 5 are out of order, so we swap them. And we end up with 6, the largest item, at the end of the array. Okay, so that's what we mean by bubble, right? So the larger items are going to end up bubbling their way up to the end. Okay, and that's the first pass. In the second pass, we're going to do another pass through the array, but this time we're going to stop at 5. Right? We're not going to bubble up all the way to 6 because we already know that that item is in the right spot. Okay, so we compare 3 and 4. These are in order, so we don't swap them. Then we compare 4 and 1. These are out of order, so we swap them. Then we compare 4 and 2. These are out of order, so we swap them. Then we compare 4 and 5. And these are in order, so we don't swap them. And after the second pass, we're guaranteed that the second largest item is in the right spot. Okay? Okay, third pass. So in the third pass, we're going to swap the 3 and 1 because they're out of order. Then we're going to swap the 3 and 2 because they're out of order. And then we're not going to swap the 3 and 4. Okay, and the result is that the 4 is now in the right spot. Okay, so we're guaranteed that the 4 is in the right spot. And we're going to keep going now and do a fourth pass. So we're going to compare 1 and 2, and we're not going to swap them, and we're also not going to swap 2 and 3. And during the fourth pass, we didn't make any swaps, right? Because we didn't encounter any pairs which are out of order. And what that means is that the array is sorted, right? So we can stop now. Right? And we know that the entire array is now sorted. Okay, and here is the code for bubble sort. Now what we see here is in our outer loop, right, where we have an integer I, which is initialized to high. Right, so high, remember, is the rightmost index, and I here controls where we go up to in each pass, right? So during the first pass, we're going to scan or sweep all the way up to high, right? And in the second iteration, we're going to decrement I once, right? So in the next iteration, we're not going to go all the way to the end of the array, but up to the second last item. Right? And then at the end of the second iteration, I is going to decrement again, and then we're going to only go up to the third last item in the array, and then so on. Okay, so that's the purpose of the outer for loop. It controls what index we during the inner loop, right? During the inner loop. Okay, so in the inner loop, you can ignore the swapped variable for now. We'll talk about the inner loop first. So in the inner loop, we make one pass through the array. Right? So the inner loop is responsible for making a pass through the array. And during the pass, we compare adjacent items. Right? So we compare items j to items j plus 1. Right? If items j is greater than items j plus 1, that means the items are out of order, so we swap them. Okay, so we swap index j and index j plus 1. Okay, and the purpose of the swapped variable is to keep track of whether we've made a swap during a particular pass. Right, so here, if we swap an item, right, we set this variable to true, right, and at the end of the iteration, if we haven't made any swaps, then we break, right, because that means we haven't swapped anything. That means the array is sorted. Okay, so that's bubble sort, and let's analyze bubble sort in terms of what happens if we give the array sorted input, what happens if we give it reverse sorted input. Okay, so if the array is sorted, then the algorithm is only going to perform a single pass, right? So it's going to perform one pass through the array, it's not going to make any swaps, and it's going to stop because it knows that the array is sorted. Okay, so in total, the number of comparisons we make is n-1, right? And we don't make any swaps, and the best case, that means the best case time complexity is O(n). Okay. Now, in the worst case, the array is reverse sorted. Okay, and this is the worst case because it means we're going to need to perform n-1 passes through the array, right? That's the maximum possible number of passes you could make. And during the first pass, right, you need to make n-1 comparisons. In the second pass, you need to make n-2 comparisons. Then you need to make n-3 comparisons, n-4, and so on. And all the way up to the final pass where you make one comparison. Okay, and that means the total number of comparisons is going to be equal to this formula that you've already seen before, so half n times n minus 1. And every time we make a comparison, we perform a swap. Okay, so that means we perform the same number of swaps. And if we take these and we remove the lower order terms and constant factors, that tells us that the time complexity in this case is O of n squared. Okay, so worst case time complexity is O of n squared. Okay, now for the average case time complexity, so what we'll assume here is that the array is randomly sorted, right? And it turns out that you can prove that if your array is randomly sorted, the average number of swaps that you're going to make is O of n squared, right? So it's quadratic. But what we can also do is show this empirically. So here I have a sorting program, and if I use make, it'll generate all the sorting algorithms, so selection sort, bubble sort, insertion sort. And what we can do is we can run bubble sort with randomly ordered inputs and see whether the time it takes for the algorithm to run grows linearly or quadratically, right? So let's try and run. Let's try and generate 10,000 items randomly ordered, and then we're going to pass them into bubble sort. And what I'm going to do is I'm going to time it. Okay, and I'm going to ignore the output of bubble sort here. All I care about is the time. So I'm going to redirect the output to dev null. So if I don't do this, what I'll get is I'll get all the numbers, right, outputted. But I don't care about the numbers. I only care about the time. So we'll just redirect the output like this. And we're going to focus on the user time. Okay, so the user time is the time it takes for the program to run, ignoring the system operations like printing. Okay, so it takes about 0.32 seconds, right, for the algorithm to sort 10,000 randomly ordered numbers. Okay, and if we double the input size, so I'm going to double the input size to 20,000 now, we see that the algorithm is going to take about 4 times as long, right? So 1.34 seconds. Okay, and we can run it multiple times just to confirm, but it does take about 4 times as long, maybe a bit more, but about 4 times. And what this tells us is that the algorithm is O(n) squared on average, right? And if I double the input size again to 40,000, we can see that, again, it takes about 4 times as long as it took for 20,000, right? So this is a classic pattern of O(n) squared algorithms. Okay, and there's a question asking if I can explain the command that I'm using. So the first part of the command is I'm calling a program to generate input for the sorting algorithm, right? So if I type gen 10 and type in R, so R is for random, it'll generate me 10 numbers in random order. Okay, and this vertical bar, what this does is it passes the outputs of the gen program into the next part of the command. Okay, so here it's going to pass these numbers into the bubble sort program. right? And the time is, it times the program, the bubble sort program. Okay, so yeah, so that's kind of an empirical analysis of bubble sort. Okay, and we saw that bubble sort is adaptive, right? Because in the best case, if the array is sorted, it takes O(n) time, right? Compared to O(n) squared time if the array is reverse sorted or if the array is randomly sorted. Okay, and in terms of the other properties, it's stable, right? So the reason it's stable is that we are comparing adjacent elements, right? And if the first item is equal to the second item, we don't swap them, right? We only swap them if the first item is greater than the second item, right? Okay, so yeah, comparisons are between adjacent elements only. We're not performing any long-range comparisons or swaps here, only between adjacent elements, and we only swap them if they're out of order. Okay, and finally, bubble sort is in place, just like selection sort, because we're not using any temporary arrays. Okay, and finally, we want to talk about insertion sort. So how does insertion sort work? So how insertion sort works is it begins by taking the first element and treating it as a sorted array, right? And then it's going to take the next element, so the second element, and insert it, so shift it to the left until it's sorted with respect to the items that have already been sorted, right? And then it's going to take the third element and shift it over to the left until it's sorted relative to the items that we've just sorted before, and so on. Okay, so here's an example. So insertion sort, it takes the first element and treats it as being sorted, right? Then it takes, so now it takes the 1 and it shifts it over to the left until it's sorted, right, with respect to the 4, right, relative to the 4. So what that means is the 4 is going to have to shift over to the right, and then the 1 is going to be, so it's going to end up where the 4 was. Okay. So we're going to end up with 1, 4. Now we try to insert 7, right? 7 is already sorted, right, with respect to the 1 and the 4. So it just stays where it is. Now the 3, we're going to need to shift over a few times, right? So we're going to shift the 7 over to the right, and then the 4, and then we're going to put the 3 right where the 4 was. Okay, and then the process continues, so the 8 just remains where it is because it's already sorted. The 6 is going to have to shift over a few spots, right? So the 8 and 7 shift over. The 5 is going to have to shift down a few spots as well. Right, so the 8 and the 7 and the 6 shimmy over, and then we put the 5 here. And then the 2 needs to be shifted most of the way down the array. Okay, so that means we're going to shift the 8, 7, 6, 5, 4, 3 over, and put the 2 next to the 1 here. Okay, so that's how insertion sort works. Right, and at the end, the array is sorted. Okay, so here is the implementation of insertion sort. Okay, so first of all, the outer loop starts at index low plus 1. right? So that's because initially we treat the first item as sorted, right? So we kind of skip that element and we look at the second element. And then for that element and the remaining elements, we need to shift them over or insert them, right? So inside each iteration, we're going to store items I in a temporary variable. Okay, and then we have an inner loop here, which is responsible for making room for the item that we're trying to insert. Right, so we're going to, so what we'll do is we're going to keep comparing the item that we're trying to insert with the item to the left, right? And if the item to the left is greater than, right, the item that we're trying to insert, we're going to shift it over to the right using this line here. All right, items j equals items j minus 1. Okay, and then we're going to keep decrementing j until we find the right place to insert the item. Okay, and this code can be a little complicated to understand. So I do have a little walkthrough of it here. Okay, so suppose we're trying to sort this array using insertion sort, right? And then we'll see how it goes. So I haven't actually marked index I and j here, but I'll fix that later today. So initially, I is going to be equal to 1. Right? Assume here we're sorting the entire array, so low is 0 and high is 4, and I is going to be initially 1. Right? So what we're going to do is going to store this item here in a temporary variable called item. Right? And then we're going to initialize j to be equal to 1. Okay, and then we're going to check if the item that we're trying to sort is less than the item to the left, right? So is it less than 4? And since it is, we're going to shift the 4 over to the right. Okay, so now it's at index 1. Okay, and now we decrement j, so j is now equal to 0, and since j is equal to 0, we've reached the beginning of the array, right? The left end of the array, and then we stop the for loop. Okay, and then we insert the item at index 0. Okay, in the next iteration, we're trying to insert 1, so we store that aside in a temporary variable, and then we initialize j to be equal to 2. Right, and what we're going to do now is compare the 1 with the item to the left. So is 1 less than, so is 1 less than 4? It is, so we're going to move the 4 to the right. So we're going to shift it over. Then we decrement j, and now we compare is 1 less than 2? Since it is, we're going to shift the 2 over. And now, since we've reached the beginning of the array, we're going to put the 1 at index 0. Okay, next, we try to insert the 5. Now, we initialize j to be equal to 3, right, to this index. But since 5 is already less, so since 5 is not less than 4, it's greater than 4, that means the 5 is already in the right spot, right? So we just insert it right back where it was. And finally, we want to insert 3. So what are we going to do? We're going to compare 3 with the item to its left. Right? Is 3 less than 5? Yes, it is. So we shift the 5 over. Then we compare 3 to 4. So is 3 less than 4? Yes, it is. So we shift the 4 over. Now, is 3 less than 2? No, it isn't. Right? So we stop our for loop and we just put the 3 at index 2. Okay, so that's how insertion sort works. Okay, so now let's analyze insertion sort. So what's the best case? What's the worst case? So the best case is again where the array is sorted. Okay, so that's the best case because every time the algorithm tries to insert an item, it only needs to perform one comparison, right? So for example, when it's trying to insert the 2, it compares the 2 with the 1, and it sees that 2 is greater than 1, so the 2 is already in the right spot. All right, next iteration, it tries to insert the 3. 3 is greater than 2, so the 3 is already in the right spot. I can just leave it there. 4 is greater than 3, and so on. Okay, and that means the total number of comparisons we end up making is n minus 1. Right, we don't make any swaps or moves, and the time complexity ends up being O of n. Okay, and in the worst case, the worst case is if the array is reverse sorted. Okay, so that's because every time we want to insert an item, right, we need to perform more and more comparisons, right, for each item. So when we try to insert the 7, right, we need to compare it with the 8, right, and then swap them. When we compare the 6 is less than everything that we've seen so far, right? So we have to swap it with the 8, then we have to swap it with the 7, and for the next item 5, we're going to need to compare with the 8, compare with the 7, compare with the 6, and then shift it all the way to the beginning, and so on. So every iteration takes more and more comparisons and shifts or swaps to complete, right? And if we total up the number of comparisons, that's 1 plus 2 plus all the way up to n minus 1, which is again half times n minus 1. Okay, and that means the time complexity in this case ends up being O of n squared. Okay, and the average case time complexity, assuming that the array is randomly ordered, is O(n) squared. Okay, and it's for a similar reason as for bubble sort. One thing I'll note is that in insertion sort, we're not actually performing swaps, right? What we're doing is we're shifting elements around, right? But the effect is that it's similar to doing a swap, right? When we're shifting, when we're inserting the 4, for example, we're not really swapping it with, the 5 and then the 6 and the 7. All we're doing is we're shifting the 5 down, shifting the 6, shifting the 7, shifting the 8, and then we're inserting the 4, right? But the effect is the same as if we were making a number of swaps. Okay, and you can also show that the average case is O(n) squared empirically if you generate a bunch of sequences like I did for bubble sort and time how long it takes. Okay, and finally for the properties of insertion sort. So it's stable, right? And the reason it's stable is similar to bubble sort, right? So we're kind of comparing adjacent elements, right? And we're essentially only like shifting or swapping if they're out of order, right? So if the items are equal, then we're not going to shift or swap anything, right? And that makes it stable. And insertion sort is adaptive, right? As we saw with by comparing the best case and the worst case and average case. So best case is O(n), average case is O(n) squared. Okay, and insertion sort is in place, right? Just like bubble sort and selection sort, it doesn't use any temporary arrays. Okay, and here's a summary of the three sorts. So you can see that bubble sort and insertion sort have very similar properties, right? They are both n squared, on in the best case, on squared on average in the worst case. But one of these is clearly better than the other one, right? So insertion sort is better than bubble sort in terms of the number of comparisons it has to make, right? If you look at an example, so let's look at an example, and we can see that bubble sort can end up comparing the same pair of elements multiple times, while insertion sort doesn't. Right, so here's an example. Let's suppose we have this array. So 1, 2, 3, 4, 8, 7, 6, 5. Right, now if we run bubble sort to sort this array, we're going to compare the 1 and 2, the 2 and 3, and the 3 and 4, and not make any swaps. Right? And then when we're kind of sorting this part, we do swap the 8 and 7, the 8 and 6, and then the 8 and 5. Right? But in the second iteration, we start at the beginning of the array. Right? So we're going to end up comparing the 1 and 2 again, the 2 and 3 again, and the 3 and 4. Right? So yeah, bubble sort isn't smart enough here to tell that we don't need to compare them again. Whereas if we sort this array using insertion sort, right, then it's not going to need to compare the same two elements, right? So it's going to try to insert the 2, it's going to see that it's already in the right place, then it's going to do the same thing for the 3 and the 4, and then for the 8. And for the 7, it's just going to shift it down once, right? And then that's it. And same for the 6, so it's going to shift it down a few times and then stop. And for the 5, it's going to just shift that down a few times and then stop. It's never going to compare the same pair of elements twice, right? Okay, so yeah, insertion sort is, in my opinion, objectively better than bubble sort. Okay. Cool. And at the end here, we have a little bit of detail about sorting linked lists. Right. So you can sort linked lists using these sorting algorithms, although it's not going to work in the same way, right? Because you're dealing with linked lists, not arrays. You can't access a specific index of the linked list immediately, right? You have to start from the beginning. But yeah, you can implement sorting algorithms for linked lists in a similar kind of style, right, to how these algorithms work on arrays. Okay, so yeah, so that's our basic sorting algorithms. Okay, and since we have a little bit of time left, we're going to start looking at our divide and conquer sorting algorithms. So divide and conquer sounds really cool. So what does it actually mean for an algorithm to be a divide and conquer algorithm? So what it means is that the algorithm splits the problem into 2 or more subproblems, right? And then it solves the subproblems recursively, right? And then it combines the results. So this sounds like recursion, right? Recursion was where we solve a problem in terms of solving smaller subproblems, right? So the difference is that divide and conquer splits the problem into 2 or more subproblems, right? Whereas with just a normal recursive solution, you can, it's possible that you break the problem down into one subproblem, right? One smaller version of the same problem. Okay, so the first the first divide and conquer sorting algorithm that we'll look at is merge sort. Okay, so merge sort was invented way back in 1945 by John von Neumann. All right, and the way that it works is it's really clever, right? So it splits the array into two equally sized parts, or roughly equally sized parts, if the array has an odd number of elements, for example. And then it recursively merge sorts each of the halves, right? So it recursively merge sorts the left half, recursively merge sorts the right half, right? And now that we have two sorted subarrays, right, we are going to merge them into a single sorted array. Okay, so that's how merge sort works, and it's really clever. And I think I have a diagram showing how it works here, right? So the array gets split into two equal halves, right? Each of these gets split into two equal halves until we have arrays of size 1, right? Subarrays of size 1. And then these subarrays, they get merged into larger and larger sorted subarrays, right? So the 5 and 2 here get merged into 2, 5, which is sorted, right? The 4 and 7 here get merged into 4, 7, which is sorted. The 1 and 3 gets merged, 2 and 6 gets merged. And then these sorted subarrays of size 2 get merged into larger and larger subarrays, right? So 2, 5, 4, 7 get merged into 2, 4, 5, 7. 1, 3, and 2, 6 get merged into 1, 2, 3, 6. And then these two subarrays get merged into one giant sorted array, and then the array is sorted. Okay, and yeah, here's another diagram showing how it works. Right, so here is the merge sort process. So we're taking two unsorted arrays, sorting them recursively. So notice here we're calling merge sort, right, within the merge sort process itself. Okay, and then the result of these merge sorts is two sorted subarrays, right? And then these two sorted subarrays get merged into one sorted array. Okay, so let's talk about the splitting and the merging, right? Because those are the two main parts of the algorithm, right? So how do we actually split the array into two halves? So what is actually happening here is we're not physically creating two smaller arrays, right? So we're not doing that. What we're actually doing is we're just calling the function and passing in different values for low and high, right? So we're calculating the midpoint of the array by doing low plus high divided by 2, right? That tells us where the middle of the array is. And then we're calling the function recursively and passing in different values for low and high, right? So for the left half of the array, we're going to pass in low and mid, right? So we're going to sort the array between low and mid. And then for the right half of the array, we're sorting between mid plus 1 and high. So we pass in mid plus 1 for our low, and we'll pass in high for our high, right? Okay, and there's a question about what if there's an odd number of elements? So if there's an odd number of elements, it's not a big deal. Just one of the halves will have one more element than the other half. So it's perfectly fine. So the halves don't need to contain the same number of elements. Okay, so because the way we're splitting the array is we're not actually creating a copy of the array or anything, we're just calculating the midpoint and passing in, we're just passing in two different sets of indices, right? The cost of splitting the array is just constant time, right? So it's O of 1. Okay, but the more interesting thing is merging, right? So splitting is really easy, merging two sorted subarrays is the hard part, right? So how does that work? So in order to actually merge two sorted subarrays into a single array, we need a temporary array, right? So we're going to create a temporary array to store the sorted sequence, and then we're going to copy the array back into the original array. Okay, and I've described the steps of how we merge here, but I think it's better if we just go through some examples. So here is one example of merging. So we have two sorted subarrays, right? We got 2, 4, 5, 7, and 1, 2, 3, 6. Okay, so now since the two subarrays are sorted, we know that the smallest element, right, overall has to be one of these two elements, right? Has to be either this element or this element. So what we do is we just compare them, right? We figure out which one is smaller, and then we copy that element into our temporary array, right? So we take the 1 and we copy it into our temporary array. Okay, and now since we've kind of used the 1, we're going to be comparing these two elements now. Right? We compare the 2 here, which we didn't use yet, and then this 2 over here. Okay, and when we end up comparing two elements that are the same, right, we take the one that's on the left. Okay, so we take this 2 here, right, and this will make sure that the algorithm is stable. Okay, so we take this 2 and copy it into our temporary array. Okay, now we're comparing this 4 and this 2. So since the 2 is smaller, we copy that down. Right, and while we're doing this, we're using an index, which I've made green here to keep track of where we want to insert the next item. Okay, so now we're comparing 4 and 3. Right, the 3 is smaller, so we copy that down. Now we compare the 4 and 6. Right, the 4 is smaller, so we copy that down. Now we compare 5 and 6. Right, 5 is smaller, so we copy that down. And now we compare 7 and 6. 6 is smaller, so we copy 6 down. And now that we've reached the end of one of the halves, so we've used up all the elements in the right half of the array, we can now take all the remaining elements from the left half and just copy those down. Right, so the 7 gets copied down. And now since we've merged all the elements into our temporary array, we can just copy them back into our original array. Okay? And here's a much smaller scale example where we just have two arrays of size 1, right? Two subarrays of size 1, just to show you how the merging works at this stage, right? So it works exactly the same way. What happens is we just compare these two elements, right? 2 is smaller, so we copy that down. And then since we've used up all the elements in the left half of the array, we copy the remaining elements from the right half, which is just the 5. So we copy that down, then we copy the elements back into the original array. Okay, and just going to go through this slide and then we'll resume on Thursday. But when we analyze merging, right, the time complexity of merging two sorted subarrays is O(n), right, where n is the total number of elements in these arrays, right? And that's because at most we're going to be making, right, n-1 comparisons, right, to merge all the elements together. Okay, and what that means is that if we have two subarrays of size 1, then that takes 2 steps, right, or 2 operations to merge. Right, if we have two subarrays of size 2 that we want to merge into an array of size 4, that takes about 4 steps, right? And if we have two subarrays of size 4 that we want to merge into an array of size 8, that takes about 8 steps. Okay, so yeah, so that's merging. And before we start, I just want to announce that I've scheduled consults for both Tuesday and Thursday after the lecture. That's because you might not have time on Thursday or you might not have time on Tuesday. So there will be consultations on both days if you want to come. Location is on the lectures page. And yeah, I'll see you guys on Thursday.